A phase shift oscillator is given, whereas GV is voltage gain of ideal amplifier. GV is a real number. In order to properly analyze its open loop gain, we need to cut the loop. At what node may the closed loop of the oscillator be cut so that its open loop transfer can be analyzed? In other words, where should we cut the loop so that our analysis of the open loop is valid? Then several options are given. So I want to remind you the theory, what the theory says, and it is given here. We have two circuits, arbitrary circuits, one circuit, arbitrary circuit, and imagine that we cut the loop here between resistor R1 and R2, and we derive this system. So here is certain voltage, and the other terminal we supply by an ideal voltage source. Now if you equate these two, Vx equal to Vy, you'll get the same circuit behavior provided this condition. So this will be the same only if R2 is extremely large, much larger than R1, or R1 is extremely small, much smaller than R2. And it all has to do with the current here. So one condition is if R1 is extremely small, for example, whatever current R2 requires can be supplied by the ideal current source E. The other option is if R2, for example, is infinity, extremely large, this means that there will be no current needed here. So if you cut the loop, this will not be a problem. Now, this condition occurs often when we have an ideal component in our loop, like an ideal amplifier, a voltage amplifier, ideal voltage amplifier. Why? Because the input impedance is infinity, which directly can satisfy the requirement that R2 being infinity is much larger than any finite number. And the other condition is that the output of a voltage amplifier is an ideal voltage source. An ideal voltage source can supply as much current as needed in order to maintain certain voltage. So the supply of this current is infinite, which then suppose that implies that the internal impedance, output impedance, is zero, which satisfy the requirement that R1 being zero, it will be smaller than any given R2. So if you have a circuit with an ideal component in it, like a voltage amplifier, it is useful to cut the loop either at the input or at the output. Keep in mind that the transfer here is just a coefficient. In this case is coefficient GV. So whatever voltage we have here, we have it the same but multiplied by GV. Now let's so this makes immediately this answer correct. Cutting loop here, and also cutting loop there is also possible, which is this answer. V3 and R and C remain together. So cut loop here. These are the two possible answers. Now to illustrate our point, let's consider one wrong answer. For example, if you want to cut the loop here. So what is the problem to cut here the loop? Don't do it. Don't do it. No. Don't do it. If you imagine that you cut the loop here, then you have a circuit which is something like this. So then GV, and then you have two like this. Now, if you analyze this circuit and you derive certain conditions, they will not be applicable to this. No. Why is that? It has to do with this current. So if you write the Kirchhoff current law for this node, you write that this current is equal to this current. While in reality, if you look at the node V2, is that this current is equal to this current plus this current. So this equation governing this node will be different than this equation governing this node. Hence, both circuits are not equivalent. Now, let's imagine that you cut the loop around the amplifier. So how our circuit will look like? Let's take one of the correct answer, for example, this one. So you cut the loop at this point. So what you have is this circuit. Yeah. And if you now look at this node, just to verify your answer, this node, the Kirchhoff current law suggests that this current is equal to this current. And in reality, here in the closed loop system, this current is equal to this current because this current is 0. Why? Because it goes to the input of the amplifier. So then here V3 is exactly equivalent to this V3. Hence both circuits are equivalent. So thank you very much.